So this is quite a title here. We're going to do tangent lines, which we talked about derivatives last time. Now we're going to kind of put it all together to write an equation of a tangent line. And local linearity, which I'm going to explain to you what that means as well. So if you're going to write an equation of a tangent line, I'm just going to kind of review this back from algebra class before we get into the calculus. To write an equation of a tangent line, you're going to need two pieces of information. You're going to need a point and a slope. And we're going to write our equations in point-slope format. You can always rearrange them if you want them to be y equals mx plus b, but we're going to start with point-slope. And your point-slope form is y minus your y value equals slope, and then x minus your x value. So I'm going to do a real quick example, again, before we get into the calculus, just so we can review having to write an equation of a line. So again, shout out some numbers to me in the chat. Just give me some numbers and I'll make up a problem with them, okay? Like, just type your favorite number in the chat, everybody. All right, cool. That's good. All right, so say this is your point and this is your slope. When you go to write that all together in the equation, it's going to be y minus your y value of your point, which in this case, that would be y minus negative 25, so that'll be plus 25, equals your slope, which is 11, and then parenthesis x minus the x value, which was 7. So that's just putting that all together. Now, if you wanted to, you could distribute the 11 and then subtract over the 25 and put it into good old y equals mx plus b, but you don't have to. You can leave it like that. Now, if you're doing a multiple choice question and they rearrange it like that, then you'll have to do those two steps. But other than that, you can leave it alone. And then just don't forget slope of a tangent line. So in order to get this piece of the equation, that slope of the tangent line comes from your derivative. All right, derivative means slope of a tangent line. It's the instantaneous rate of change. Do you guys remember Alice going for the walk? We kind of like zoomed in on 1 hour for her and found her instantaneous rate of change. That's what all this means, okay? So let's do an example. And you may have noticed I called this A. I'm going to do like parts B and C with this, so we don't have to start over with a whole new function. So I'm going to use all the same information. So we're going to write an equation of a tangent line, so it'll be in this format, for this function at this point. So again, you always need two things. You need a point and you need a slope. So I usually set it up so that I can fill that in. Now, my point is going to be 1 comma something. And then my slope is going to come from the derivative. So to get this y value, all you have to do is plug 1 into the function. So if we plug 1 in here, 1 squared is 1, times 2 will be 2, plus 1 would be 3. So that is our point. And then again, slope comes from derivative. So let's review this formula. It is limit as h goes to 0, f of x plus h minus f of x all over h. And remember, it's just a whole big bunch of algebra. Without this limit, it's just an algebra problem. Okay, so we're going to do this for this function. So limit as h goes to 0. And the first step is you're going to plug x plus h into the function. So we will have 2x plus h squared plus 1. Sorry, the desk I'm writing on has all these grooves in it, and sometimes when I'm writing, it just like sinks into the table. All right, so we plug x plus h into the function, then we're going to subtract the whole function. So I'm just going to subtract this whole thing, and then it's all over h. So this is the step where this is going to get really expanded, but remember, it's going to get large for like 1 second and then everything should cancel out. So this first piece, x plus h squared, means this. I'm just going to write it off to the side. And if we multiply that together, we're going to get x squared plus 2xh plus h squared. So that is this piece, and we're going to distribute the 2 through that. So 2x squared plus 4xh plus 2h squared. So that is this entire first part. All right, then plus 1. And then I'm going to distribute this negative sign into these parentheses. So minus 2x squared minus 1, all over h. All right, guys, what's going to cancel? Just go ahead and type it in the chat. We want stuff to go away. This is the step where things should leave. All right, yep, good. The 2x squareds are going to go. And good, the 1s are going to go. And I think that might be it, but that's good. Now, everything that's left has an h in it. So yes, the h is going to cancel. And I get people that will try to skip this next step. I recommend against that. Just go ahead and factor out the h, because if you don't write this, you're not going to see what's left if you just try to cancel it out. And remember, at the end, you should plug in 0 for h. So people also forget to do that if they skip this step. So it's only one more step. Just write it. I factored h out of the numerator. They're going to cancel. And here's our derivative. Plugging in 0 for h leaves me with just 4x. So that is our derivative. Now, to get our slope of our tangent line, we want the derivative at x equals 1. So we're going to plug 1 into our derivative, and that will give us 4. And then just write your answer. This is your point. This is your slope. So our equation would be y minus 3 equals 4, parentheses, x minus 1. Now I want to take a minute and just show you on the calculator what this graph looks like. And we're going to talk about what this means here. Oh, I'm sorry, go ahead.
Sorry, can you re-explain why it's at x equals 1 and where you got the 1 from again?
Oh, that is actually just going to be given information in the problem. Like that.
Okay, I thought I missed a calculation.
Yeah, that will be, here, let me get another color here. I get asked that a lot in calculus because when we do calculus problems, they tend to like be tons of information and fill the whole page, and then you forget what was given to you and what you provided. This part I'm going to highlight in pink here was given. So that would be provided, and then everything else I wrote after that is like the work I did on the problem. I get that calculus is like number explosion. It's hard to remember what was what, but that was told to us. So we've got that. All right, so I'm going to show you this function on the calculator, and then we can talk a little bit about what this means, local linearity. So I'm going to go to y equals and type that function in. What was it? 2x squared plus 1. And so we will go to the graph, and it's going to be a parabola. What I want to do is zoom in on the point at 1. So I'm going to zoom in on that point. So I'm going to go to zoom in, and I'm going to try to move my cursor close to where that is. That's pretty good. All right, so still looks like a parabola, right? So let me zoom in again. And again, I'm going to try to zoom in on right about 1, 3. That's good. So does it look like a parabola anymore? And I can even zoom in again. But if I zoom in far enough, what does this start to look like? Yeah, good, it's a line. And you can do that with any function. If you zoom in far enough, you get local linearity. Local means really, really close to a certain point. Now I zoomed in on 1, and so if we get really, really close to 1, the function is locally linear. And so what that means is I can use this line to make approximations for this function, as long as they are really close to the point of tangency. They have to be really, really close to the point where you wrote the equation. So for this line to work, I need to do approximations that are really, really, really close to 1. So I'm going to call this part B. Let's approximate f of 1.2. So the reason this line is going to work is because I wrote the tangent line at 1, and 1.2 is really, really, really close to 1. Now all you have to do is plug 1.2 into the function, or I guess I should say the line, into the tangent line. So all we've got to do is plug in 1.2. Oh, I should use approximately. And then just get y by itself. So you would just have to add over the 3. So y is approximately this. That would be your approximation at 1.2. And again, the reason that that worked is because 1.2 is really, really close to 1, which is where we wrote the equation of the tangent line. Now say you were asked to approximate f of 3.9. This equation is not going to work anymore. Oh, and I would do nothing to that. I would just leave it alone. If you have a free response question in calculus, you don't have to evaluate anything at all, and you're better off not evaluating for several reasons. First of all, the AP exam is timed, so you don't want to waste your time doing this. And secondly, if you mess this up at all, then it'll be wrong. So I would just do nothing to it. That always bothers people at the beginning of calculus, and then by the end, you'll get used to it. It's less work, so it's nice. Now, if we want to approximate at 3.9, this equation's not going to work because our point of tangency was at 1. We're going to need to write a new equation. Where should we put our point of tangency? If we want to approximate 3.9, what should be our point where we write the equation? Yeah, good, 4, because 3.9 is really, really close to 4. So I need a new point and a new slope, because again, this equation's not good. So to get my y value, I'm just going to plug 4 into the function. So if we plug in 4 for x up here, that will be 4 squared is 16, double that is 32, plus 1 is 33. And slope comes from the derivative, so we want the derivative at 4. And so the reason I made this an A, B, and C problem is so we wouldn't have to find another derivative. We just take 4 and plug it into our derivative, which is right here. So 4 times 4 would be 16. And now I can write a new equation. So it would be y minus 33 equals 16 x minus 4. And then if we want to approximate f of 3.9, all we've got to do is plug in 3.9 and then get y by itself. So y is approximately 16 times 3.9 minus 4, and then I've just got to add this 33 to the other side. So let's try, we'll do one more and then I'll give you a break here. All right, so if that is our function, we want to approximate f of, let's see, let's do negative 2.9. where should we write our equation? What should be our point of tangency? Yeah, good, cool. We want -3. All right, so we need a point and a slope. We need -3 something, and then our slope. To get the point, you're just going to plug -3 into the equation. So that would be -1/3. Slope comes from derivative. All right, for the sake of time and because I'm not trying to torture you, I will not make you go through this limit process again. But you would have to do this limit process in order to get the derivative. Do you guys all understand that? I'm going to let us skip that and I'll just give you the derivative for the sake of time here. But you would have to go through this whole process again to get your f prime of x. I'm just going to give you this one. So f prime of x is -1/x². Oh, you're fine. No, thank you for asking. I'm asking for an approximation at -2.9. So we needed our point of tangency to be really, really, really close to -2.9. Again, that's because your functions are only locally linear. You have to zoom in really, really close on the point for it to approach something that looks like a line. So you have to be really close to that point or the approximation won't work. In other words, the further away from the point of tangency you get, the less good your approximation is. Like if you have a function that does this, and here's your point of tangency, really, really close to there, the line and the equation are very close to each other, but the further away you get, the further apart they get, and then the less good your approximation would be. So you have to be really, really close. All right, so this is our point. Slope comes from the derivative, so we would want to do f prime of -3. Again, -3 is our point of tangency. That's where we want to write the equation. And if we plug -3 into this derivative, which again, I didn't make you work to find, I just handed it to you, okay? -3² would be 9, so that would be -1/9. So this is our point, this is our slope. If I put that all together in the equation, it will be y plus 1/3, and it's minus -1/3, equals my slope, parenthesis, x plus 3. So that's our equation. And to do your approximation, all you need to do is plug -2.9 in for x. So this will be -1/9, -2.9 plus 3. And then I've got to subtract this 1/3 over to the other side. So I'm going to put -1/3. And that's just to get y by itself for the approximation.